Remind me what it was that we decided makes a function a linear function. How do you know it when you see it?
It's constant.
What's constant? There's that word, it, again. Yes, slope. There we go. Right. And slope has what other name we otherwise know in our course so far? Rate of change. In particular, in our course at least, the average rate of change, right? Because we're not ready until calculus to talk about instantaneous rate of change. But the average rate of change is constant everywhere. So that's how we recognize it from its change properties. Right? No matter which 2 points that I pick on the graph of a linear function, the average rate of change of the function between those 2 points always gives me the same number, and that same number is indeed the slope. That's what we call the slope of that linear function. So one of the main goals, and we've done a little bit of this already when we talk about average rate of change, one of the main goals for this section for us today is to not only be able to understand linear functions in formulas, in graphs, and in tables of data by looking at average rates of change, but also to be able to pull meaning, contextual meaning, out of the slope and the intercept parameters. What does this number tell me about the situation? What does this slope mean? What does intercept actually mean? When our functions are more than mathematical, they're practical, right? How would we communicate to, our boss or whatever who might not be sitting in a pre-calculus class about what the meaning of a slope number is, what the meaning of an intercept number is? And it's going to be the same thing when you talk about quadratics also. We have this familiarity with what quadratic functions look like algebraically and graphically, but to be able to pull some meaning out of the parameter values that go into it is what we're going to spend some time talking about when we get to section 1.5 today. So with that, let me invite you in your groups to start on activity 143. So let me scroll down to it and make sure we're all looking at the same one. If you start this activity and find that you're getting kind of turned around, you might want to go back to 1.4.2 and talk about the first couple parts of that one first, just to clear some things up. But if you're ready to go on 143, I encourage you to start with 143. So in this, we know something about the summit of Mount Kilimanjaro. It has these ice fields and measurements of the ice cover in 2 different points in time, the year 2000 and the year 2007. And based on those 2 data points, we want to be able to make some predictions and extract some meaning about how the ice cover on top of Kilimanjaro is changing over time. You started out with some data about the area of the Kilimanjaro ice cap in 2000 and 2007, and then you're asking questions about making a linear model and interpreting the parameters of that linear model. Right? So first of all, my recommendation, anytime you're faced with a block of text like this and you need to extract mathematics from it, you know by now I like data tables for this. Right? So what 2 data points do we have in this table based on what you read in the paragraph? 2000, so the year 2000. And what was the area in 2000? 1951, 1951. And what's the other one? 2007. And the area there was 1,551. 55, sorry. My eyes are not what they used to be. There we go. Okay, so before we move forward with these 2 data points, what am I going to say? So what are the units on the A variable?
Meters squared.
Square meters, right. This is the area of the ice cap, and so it's measured in square meters. What are the units on T? Years. And how is T measured?
By years from 2000.
By years from 2000, right. So include that in your units so that, what does that allow us to do, by the way? Years.
Smaller numbers.
Use smaller numbers, exactly. That is the whole reason why we pick a different origin for the time variable very often, because it's harder to work with numbers like 2007 and 2000 than it is to work with, what would the t values be if it's measured in years? Yeah, the t values are 0 and 7 that we would use instead. So that's a convenient simplification tactic, right? It lets us work with smaller numbers. Okay, right. And so the question is, find a linear model whose output is the area and whose input would be the year, number of years since 2000. So what is being posed as, I want to go to the graph next, actually. What is that set up as the horizontal independent variable? What is it set up as the vertical? Which is which?
The vertical is the area.
Vertical would be the area.
And then the horizontal is time.
Horizontal is time. So again, this is measured in years since 2000. And A here is measured in square meters. Okay, great. So what model, what linear model, what function written out as a formula did you find for this? Let's jump straight to your answer, and then I want to hear about your process.
We found that the f in this case
Uh-huh.
is negative 56.
If you got the number negative 57, and you wrote this function, a equals negative 57, f of t equals negative 57, what would the graph of that look like?
Straight horizontal.
A straight horizontal line. So why does that, for me, cause some concern? Does that horizontal line match the behavior we're expecting to see in this data?
No,
Why not?
because it's not changing.
Right. We're not seeing, well, in fact, what's not changing here?
Yeah.
The t-values can change across this horizontal line, but the a-values, right, the a-values are not changing. So this would represent an ice cap that's neither growing nor shrinking, right, just staying the same over time. And that doesn't appear to be what's happening in the data set. This is the great thing about story problems, right, is that you have this point of practical reference to look back to. And at every step of the modeling process, you can say, does this line up with what we know about this situation, or is there something else going on? So what are we missing here? Maybe we'll talk about where did this number negative 57 come from? How did you get that?
Average rate of change.
It's an average rate of change, which is the same as the slope, exactly. So to find that average rate of change, you did what?
You took the data,
Took the 2 points, yep, and did what? Subtracted. So when I subtract 1555 minus 1951, what did you get there? 396, sorry, negative 396. So again, looking in the data table, that's what happens to this number to turn it into that number. We subtract 396 to go from there to there. And that becomes, where do I put that in my slope? Top. Great. So upstairs, minus 396. What goes in the bottom? 7. Because?
0, or 7 minus
7 minus 0. Yeah, exactly. Yep. So to go from that t-value to that one, we're adding 7. That becomes the denominator. And so you got this 57 number, negative 57 number, by dividing negative 396 divided by positive 7, right? And if you like, that's negative 56 point, what did you say it was? 29. I would say 2857143. Dot, dot, dot. Anyway, so it's a rational number, right? It's 396 over 7 just made negative. Great. So now my slope is in here. But what is this equation still missing? There's more to a linear function than just its slope. What else do we have to specify? We have to specify an intercept, right? And I'm going to claim that in this problem, at least, that should take us almost no time to do. What is the vertical intercept of the graph of this particular linear function?
At 0.
At when what is equal to 0?
At 2000.
Yeah.
Is 0.
So at that point right there,
Yeah. The area was 1950.
1951. And that's the intercept, the vertical intercept of this function, because it's the point at which the horizontal coordinate is equal to 0. Right? That's how you find a y-intercept for any function. You just say, what is y when x is equal to 0? Because all the points on the y-axis, or the vertical axis, are the points where the horizontal coordinate is equal to 0. So anytime you see a 0 in the x-coordinate, you're at the y-intercept.
Right.
And vice versa. Right? If you see a 0 in the y-coordinate, that must mean you're at an x-intercept. Right? So I claim that we don't have to do any work to justify that this is, in fact, my vertical intercept. Because we know that our line is going to go through that point, 0, 1951. We so far know roughly, again, what the slope is that we need. We now know the intercept. So how do we put those pieces of information together into a formula for this function?
Would it turn just negative 57t plus 1951?
Yes. That's the old y equals mx plus b template coming back to save the day. Right? Where the role of m is played by our slope, this number. Right? The role of b is played by our vertical intercept. And the role of x is played by our independent variable t. Right? So there is my linear model for this ice shelf melting. Right? F of t is negative 57t plus 1951. And so if we were to graph this, what do we expect it to look like? It's a straight line, but what do we know about that straight line?
Decreasing.
It's decreasing. And what is it that tells you that it's decreasing?
Negative slope.
The slope is negative, exactly. So we end up making the same kinds of observations a lot in Chapter 1, right? Because anytime we're talking about slope and we get a negative number, something is happening that indicates a decreasing pattern, right? A relationship between increasing one of my quantities correlating to a decrease in the other, and vice versa, right? And for a linear function, the average rates of change are the same everywhere. And so once I know that my slope is negative between 2 points, it's negative between all points for a linear function. Right? And so a linear function with a negative slope is decreasing everywhere. Right? We don't have this weird behavior like we talked about at the end of our last class, where it can go up and then go back down. Right? Linear functions don't do that. And so somewhere else on this graph is our other data point, right? 7, 1555. Great. Okay. So I want to pick out just maybe one of the pieces from later in the problem. Let's maybe look at, let's look at part B. What do the slope and intercept mean? Let's start with the intercept, because I think we may already have mentioned it. What does 1951 correspond to here? What does it tell us about Kilimanjaro?
The area in 2 years.
The area in how many years?
2 years.
T years. Well, that's A of T, right? The whole thing tells me the area after T years. How many years is T if we're talking about the intercept?
2000.
Right, the year 2000. So that then be a good interpretation for the meaning of the number 1951. So I'll sort of write that as a sentence here. In the year 2000, which is when T equals 0, I'll also put that in parentheses here, the area of the ice cover was 1,951 square meters. So that's the intercept. The intercept is usually the simpler one to explain to somebody, right? It's just, sometimes people think of it as where are you starting, right? At the origin of your horizontal variable, what is the value of the vertical? So what about the slope? The slope is the more interesting one to me, right? This number, let's call it negative 57 now, just so that we can talk about it more easily. Negative 57 what? What are the units on that slope, first of all?
Meters squared per year.
Meters squared per year. How did you know that? Where do those units come from?
It's the average rate of change
Uh-huh.
in a year.
Yes,
On
true.
Yeah.
Right, and so the reason that it's meters squared per year is the meter squared is coming from the vertical value, right? We took 1555 minus 1951. Those are both meters squared quantities. We subtracted them. This numerator is a meters squared quantity. And when I subtract the 7 and the 0, those are both numbers of years. So when I subtract them, I get a number of years. And so the units on my slope are staring at me in the face right there. Meter squared divided by years. So this is what I always recommend to people. The first thing to do in interpreting a slope is get your units right? Keep the units in your slope fraction, and it'll pop right out at you. So now that we have the units right, how do we write a sentence that tells me the meaning of the number negative 57? How would you describe that?
In an average year, the area of the ice cover decreased by negative 57.
Awesome. In an average year, and I like the use of the word average there, right? We talked about this in our last class, right? Because that there we're being really careful, right? In an average year, the ice decreased. And we might even add the words at a rate. At a rate of 57 square meters per year. Right. Now, if it's true that this function really should be modeled by a linear function, then we could actually get rid of the word average. We could say every year the ice is decreasing at a rate of 57 meters squared per year. Right? Because why? What's true about linear functions? It's constant. The average is the everything for a linear function. Everywhere the rate of change is the same if the function really is linear. But we don't know. We only have 2 data points to work with in this problem, so we don't know if this function should be linear after all, or if there might be some other behavior that we're not seeing in between these data points or beyond these data points and so forth, right? So keeping the word average in there is, I think, an appropriate way to make sure you're hedging, right? That you're not saying more than the data points suggest that we can say. All right, so last question I had before we move off of this one. How could we use this model to predict the vanishing of the ice cover? What does that mean? This is part D. So what I would say is a sort of a less formal way of doing this is saying, well, we start out in the year 2000 with 1,951 square meters of ice. And every year we're losing 57 of those square meters. So how many years is it going to take for all of the 1951 to go away? just divide the two. 1951 over 57, or we could make this positive, right? It's going to take about 35 years for the ice cap to disappear. And so what year does that correspond to?
2035.
2035. That is the informal way of doing this, and it gets us a completely correct answer, right? Let's, for the sake of using the same kind of reasoning in other modeling situations that aren't linear, how could I have done that using the formula?
You could plug in 0
For?
f of t or a.
Yes, exactly. So that, I think, is the way that the author has in mind when he writes this problem. And because you're saying that what it means for the ice to vanish is it means that the area of the ice becomes 0, right? And so we want to know when. So we know the value that we want for A, and we're asking what value do we need for T in order to make that happen, right? And so we know how A and T are related. That's what this formula does for us, right? So we'll just come back here and place a 0 where we see the A, and then we'll just do the necessary algebra. So A equals f of t equals minus 57t plus 1951. Right, and we replace the A with a 0. And let's talk through the 2 steps that we would need in order to solve this equation for t. What's the first thing I'm going to do? Subtract 1951. I missed a plus sign in the middle there. Yeah. So subtract 1951 from both sides. And then what do I have to do after that? Divide by negative 57. So we can see Anthony's arithmetic jumping right out at us there in the end. That's why that reasoning got us an exactly correct answer, right? T equals 35. Because it's the same reasoning we would have to do if we set up this linear equation with a 0 on the other side and then solve for t.